Hello, and welcome to this introduction to code workbooks in the N3C Enclave. Code workbooks are a hybrid graphical interface where you can write code in Python, R, or SQL to analyze and visualize data. Code workbooks aren't the only application for writing code in the Enclave. There is another application known as code repositories, but code workbooks provide most of the same features, including code and data branching, in a friendlier interface. Speaking of interfaces, you might notice similarities between code workbooks and familiar tools like Jupyter Notebooks or RStudio, but there are plenty of differences as well that we'll be getting into. Before we get too far, I want to make note of the training portal available in the Enclave, linked from the Enclave homepage under Training Material. As we go, I'll be referring to other training modules here. Additionally, you should already be familiar with N3C, navigating the Enclave, the OMOP data schema, and creating and working with concept sets in the Enclave, all of which are essential skills for working with N3C data. If you need to brush up on these, check out the orientation modules, Enclave organization, and especially the Intro to OMOP and Contour module, which is the logical predecessor to what we'll discuss today. So let's get started by opening back up the brand new code workbook I recently created. We're presented with the option to import some data, but I'm going to skip that for now. Instead, let's import a dataset the regular way, by clicking Import Dataset in the main interface. Let's import the concept set members table, which as you know contains all of the concept sets defined by the N3C community for use in the Enclave. With this dataset node selected, we can see a preview pop up down below. There's one thing to note here already. Notice the section that says concept set members as concept set members. The first is the name of the dataset in the Enclave, whereas the second is the name for this workbook. We could, for example, call this table Concept Sets All in this particular workbook. We can work with imported datasets like this one by creating what's known as a transform with some code, either in Python, R, or SQL. Let's start by creating an SQL-based transform that filters the table to the non-influenza pneumonia concept set we created in the Intro to OMOP and Contour tutorial, which has code set ID 7613477708. The code for that is pretty simple. Select star from concept sets all, where code set ID equals 7613477708. Of course, we could also select by the concept set name and is latest version equals true to always select the latest version of this particular concept set. To see the filtered result, we can just click on the big preview button. Now we can see that there are two nodes in our notebook, showing the imported data and the data provided by our code. When we have the code transform selected, we can see in the lower panel the code itself, but also the preview of the result, and if our code had anything to print or generated an error, it would show up under logs. This transformed dataset got the name unnamed, so let's instead name it to Pneumonia Concept Set. Now let's import another dataset, this time the condition occurrence table from the Cynthia notional data. Like the SynPuff data, Cynthia data don't contain any real patient information. The advantage of the Cynthia data over the SynPuff data are that they better match the columns of the real N3C data and even include some notional or fake COVID-19 test results. Notice that our newly imported data also show up as a node in our graph. We can rearrange these nodes by dragging them, and if we want, we can even add colors to help us disambiguate them. Let's color our two input datasets blue to help keep them separate. We do this by creating a color group, giving it a name like input datasets, and adding the nodes as needed. Again, we can hide the preview panel below by deselecting nodes by clicking on the background. And in the lower left, there are zoom controls such as zoom to fit. We can also zoom in and out with the mouse scroll wheel or touchpad gesture equivalent. Now let's add another transform. This one will take in both the pneumonia concept set we filtered to and the newly imported condition occurrence table, and match all of the rows from the condition occurrence table where the condition concept ID matches any concept ID from our pneumonia concept set. We'll do this with an inner join, effectively pulling out all of the different kinds of pneumonia cases from the condition occurrence table. We can create a new transform either with the New Transform button in the upper left of the interface and then select the inputs for it, or we can start with an input like we did before and use the big blue plus button. This time, let's create an R code transform. One of the unique features of code workbooks is the ability to easily mix SQL, R, and Python code in the same analysis pipeline. We'll see some Python examples in a minute. Let me go ahead and zoom to fit to help make it clear what's going on. Our R transform contains the skeleton of an R function, with the pneumonia concept set table as an input, and the name of the function is currently unnamed. Since this transform will produce a table of pneumonia conditions, let's rename the function to pneumonia conditions. Notice that doing so also renamed the dataset in the code workbook to the same name. Similarly, if we rename the dataset in the interface, the R function name is updated to match. Because pneumonia concept set is an input to this function, there's an arrow displayed between the two nodes indicating that relationship. If we also add condition occurrence as an input, another arrow will be drawn. And if we again remove that input, the arrow goes away. The other way to add an input to a transform is to use the plus button in the input section, which lets us select an input via the GUI to have added to our R function code. Before we go on to write some R code, let's first investigate the data types these data nodes are representing. For example, if I select the SQL node we created earlier, we can see that the input concept set members table is a Spark data frame, indicated by the little orange star icon. This is because all data tables in the Enclave are stored and handled by Apache Spark, a high-performance distributed computing framework for working with large datasets, where tables like this one are actually split up and stored across different servers or computers behind the scenes. Transforms like this one similarly return Spark data frames, so you can imagine a Spark data frame traveling along the line as input to our R transform. However, if we inspect our R transform inputs, we can see that the incoming pneumonia concept set is actually coming in as a regular R data frame. This conversion happens when the data reaches the R transform. If we want, we could instead choose to leave it as a Spark data frame, but then we'd need to use the Spark R library in R to work with the data in that format. We'll revisit this in a few minutes, but for now we'll leave this conversion, and just note that it's only when the data reaches this R transform that the conversion happens for us automatically. Similarly, we can see that the condition occurrence table is being converted to an R data frame from its native Spark type, and there's a warning involved in this conversion because Spark data frames can have column types such as long that R data frames don't have. Usually this isn't an issue, however, so we won't worry about it for this brief introduction. Now, since these are both regular R data frames, we can use regular R code here to do our inner join with the merge function. We'll also include a debugging print statement to see the structure of our merged result before returning it. Once the preview is complete, we can see it in the Preview tab below. And since our transform did some printing, we can see the result of that in the Logs tab. What if instead of using base R's merge function, we wanted to use the inner join function from the popular dplyr library? That's easy enough. Just like in regular R, we can load the dplyr library with library dplyr near the top and make use of it in the code. In fact, if we wanted, we could define other R functions in our transform and call them from the main function. We just have to define them below, as it is the first function that defines the inputs and outputs for the transform. Now let's illustrate the exact same thing, but this time we'll do it in Python. We can create a new transform from our pneumonia concept set, selecting to Python, and I'll move it down and center my view to help keep the code workbook clean. Next, I'll add the condition occurrence table as an input to the skeleton function, and rename the function to pneumonia conditions 2, which also renames it in the code workbook interface just like before. There's one big difference from the R transform here. The input tables are coming in as Spark data frames without any conversion, which is the default for Python transforms. We could either work with them with the PySpark library, or convert them to pandas data frames when they reach this transform. We'll do that for now, using the pandas library to do the join and printing some debug information. Just as before, we can use the tabs below to see the computed preview after it's been computed, as well as any printed logs or errors. This is a good time to mention an important rule that applies to both R and Python transforms. They must be implemented as a function that takes one or more data frames as input and returns a single data frame as output. The returned data frame could be a Spark data frame if you didn't convert the inputs from Spark to begin with, or the returned data frame could be a Pandas or R data frame, in which case it will be converted to a Spark data frame on its way out automatically. Note that sometimes in R and Python it's possible to produce outputs that look like data frames but aren't. The summary and table functions in R, for example, do not produce data frames, so cannot be used as the return from an R transform. Crafting a true data frame for returning may thus require a deeper understanding of the code you're writing than in some other environments. Don't forget that in R there are several ways to return from a function aside from an explicit call to return. This is also a good time to talk more about Apache Spark. As we've noted, it's possible to convert data frames from their native Spark format to either R or Python Pandas data frames. The advantage of doing so is that it's easier to work with the data in these more familiar formats. The downside, however, is that it's only possible to do this conversion if the data are small enough to fit on the cloud-based server allocated to run the R or Python code itself. Both of the tables we've seen here are only a few million rows, so this hasn't been an issue. But some N3C data tables contain billions of rows, and attempting to read these as R or Pandas data frames will result in an out-of-memory error. In these cases, you'll need to use the PySpark library in Python or the SparkR library in R to work with the data. We won't discuss using these libraries here, but in the training portal you can find modules with links to tutorials and example code. Just search for PySpark or SparkR. When using SQL transforms, Spark SQL is the dialect being used, so those are already Spark enabled and include a complement of Spark-specific SQL functions you can read about in the Spark API. Lastly, when using Apache Spark functionality, there are tips you might find helpful to make your code more performant. The training portal module Troubleshooting Slow Build Performance covers some of these, though with the recent upgrade to Spark 3, several of these optimizations are now automatic. Of course, you might be able to use the Contour GUI tool to filter to a smaller subset of data first before importing that data into a code workbook, avoiding the need to worry about Apache Spark altogether. Now that we've seen the basics of writing transforms in code workbooks, let's explore some more features of the interface. If you are an R or Python user, you are likely to use multiple R or Python transforms, in which case you might want to use the global code feature to write code that should be included in all such transforms. For example, rather than calling library dplyr for all transforms where I want to use the dplyr library, I could include that line here, and the same goes for my Python Pandas library import. Next to the Global Code tab is the Console tab, where we can use an interactive R, Python, or SQL console to run short test lines, much like you would in other environments. However, because of the behind-the-scenes interactions with Apache Spark, this console isn't as responsive as you may be used to, and not all functionality will work as you might expect. Notice that down below there's a variables drawer listing the variables available to the console and allowing for impromptu conversions. Now let's talk a bit about saving results from a code workbook to a dataset that can be used in other places in the Enclave, possibly even other code workbooks. If we recall, when we first imported the concept set members table, it actually had two names: the name it is stored under in the Enclave as a whole, and the internal name we use for it in this code workbook. The results of our later transforms only show the internal name by default because the resulting datasets are not persisted outside of the notebook. To save them, we can turn on the Save As Dataset switch, which gives the file to be saved a boring default name that we can change. I like to do this by highlighting the internal name again and pressing Enter, which will trigger the interface to ask if I'd like to update the external name to match. Perhaps in a future update, the external name will be matched by default. The location of the resulting saved dataset is controlled by the Output dropdown up above, though the default of a subfolder with the same name as the code workbook inside of a Workbook output folder is almost always fine. To trigger the generation of the dataset, our Preview button has turned into a Run button. Unfortunately, now when we run this transform, we are running into a real error, the result of the warning we saw earlier. The specific error shows an unsupported column type of integer 64 when trying to save the result as a Spark data frame outside of the code workbook. We could investigate this by taking a look back at our debug printout showing the structure of what we're trying to return, but that's been masked by all of the error logs. To hide these, instead of returning result, we'll return null, or none if this were a Python transform, and try again. Returning null saves the result as an empty table, and we can again inspect the logs to see that the condition source value column has the offending type. We can either remove that column or convert it to a basic integer type before returning. Let's do that and try again. Now our transform again runs successfully, and this time our dataset has been saved in the output folder. Let's go and take a look at it by using the breadcrumb navigation to open the Workbooks containing folder, then looking inside the subfolder created for dataset outputs. One very cool feature of transforms that save their output is that they allow the addition of a description field where we can enter markdown text that travels with the saved dataset. Let's add a description to this dataset describing its contents. When finished, the description is rendered in the Description tab, but we can also see it as part of the node overview, and it even follows along with the dataset to the dataset preview. If the dataset were imported into another code workbook, it would be viewable there as well. These transform-level descriptions are thus a great way to add documentation to your research artifacts. Speaking of generating outputs, we haven't yet mentioned producing graphics. While code transforms usually produce data frames as outputs, it's also possible for them to generate figures with libraries such as ggplot2, matplotlib, and seaborn. Let's have our R transform generate a plot. I'll start by putting the call to library ggplot2 in the global code section. The resulting image is shown as a thumbnail in the transform node and can be shown in a larger scale by zooming in on it, and from there included in other Enclave resources like reports. In fact, you'll need to do so in order to export results from the Enclave for publication, whether as an image like this one or as a summarized data table. For details on how to properly download results for sharing, including for publication, check out the How to Download Results Outside the Enclave training module, and you may also find advice on manuscript preparation useful too. Remember, it is against N3C policies to take screenshots or download figures directly without going through this review process. Earlier we mentioned using libraries in R or Python code like ggplot2 and pandas. In fact, hundreds of common packages for these languages are available, but you may need to take extra steps to utilize them. The libraries that you can import in your transforms are installed in what is known as an environment. We can see the environment configuration under the Environment dropdown in the upper menu bar. This shows that I am currently using the default environment profile. To see which packages are installed in this environment, I can click Customize Spark Environment. On the right are the list of packages available for import, and on the left are the other pre-built environments we might use. The Profile High Memory environment, for example, includes the same packages as the default, but with more memory available for pandas and R data frames or other in-memory datasets. The GPU profile provides access to GPU compute resources for deep learning applications as well as the TensorFlow and Keras Python packages. If we want to add to or modify the list of installed packages, we can choose a starting profile and select Customize Profile. This gives us the option to select specific versions of packages, remove packages from the installation, and add new ones by searching for them. Behind the scenes, these packages are handled by the Conda Package Manager, so R packages are generally prefixed with either R or Bioconductor to distinguish them from their Python counterparts. After modifying the package set, we can trigger reinstallation of all of the packages into this now custom profile by clicking Update Spark Environment. From there, a new Apache Spark session is created, and eventually the custom environment will move into an initializing environment state before it's ready for use. Be warned that this initializing environment step can take some time, and in rare cases may not complete at all. The reason for this is that while pre-built profiles such as the default or GPU profiles are quick to start because they are pre-built, custom environments require installation of all of the listed packages from scratch in an on-demand fashion. This is true even if your environment customizations are minor. The time it takes to initialize a custom environment thus depends heavily on the number and nature of packages used for the custom profile. In fact, if you need a single specific package for your workbook, you are better off to customize the light profile, which includes fewer packages overall than the default profile. Some research project teams have requested pre-built profiles for specific sets of packages to avoid startup wait times for their notebooks. You can do so as well by submitting a request through the Help and Support issue reporting workflow. The Enclave developers are actually working on better tooling for environment management, so be on the lookout for changes to this part of the interface. I'm also told that soon the light profile will be made the default for new code workbooks, making it more straightforward to customize the default profile and not have to wait quite so long for it to initialize. I mentioned that the Conda Package Manager is used behind the scenes to manage these package installations. Automatic choices for versions are thus chosen by Conda, and while this usually means latest, that's not always the case. Once an environment has initialized, you can see the exact versions of all packages and their dependencies that have been installed by clicking View Resolved Packages. If you are reproducibility minded, you might then click on the pin icon to always use those specific package versions in the future. Speaking of Conda, one of the longer steps during environment initialization is when Conda searches for a set of mutually compatible package versions. If this is hard or impossible for the packages and versions you've chosen, the environment may hang on the initialization step but not report an error. You may also see the initialization step hang if the Enclave is very busy and not enough compute resources are available. In that case, you can try using a high memory profile, since those are part of another resource pool. In the end, if you're unable to troubleshoot an environment-related issue, please do submit a request for help via the Help Support Issues Tracking system, and be sure to note what profile you're using and any customizations you've made. While we're on the topic of packages and the help system, if you want to use a package not available in the environment customization list, you can request to have it added via the Help and Support Issues system as well, and the Enclave support team will do their best to ingest it. There's no guarantee that it can be, but packages already available on Conda channels, CRAN or Bioconductor or PyPy have the best success rate. The last feature of code workbooks I want to show is the usage of templates. A template is a kind of reusable transform node where the code has been wrapped by a graphical form, allowing users of the template to modify the code via parameters from the form. To show an example, I'm going to add a new transform to the condition occurrence dataset, but this time select the templates option. All templates published in the Enclave are browsable under template folders, but due to project-level restrictions required by N3C's data access model, you may not be able to use templates created by other teams in their own project workspace. The Knowledge Store folder, on the other hand, is a place where researchers can submit templates for access by everyone. The template that I want to use is the Sample Persons template, which according to the description subsamples rows of a dataset according to a random sample of person ID column entries. Such sampling can be useful while developing analysis pipelines on smaller datasets for efficiency. Clicking Apply Transform creates the new transform node and presents the form where we can enter parameters. For example, we can change the percentage of person IDs to keep to 10. If we click the Toggle View button, we can see the code view of the transform. Note that the value 10 is taken directly from the form view, and changing it back adjusts the code as well. Template nodes don't allow you to edit the code itself, unless you first convert the transform to a regular code transform under the Actions dropdown. Templates can also use parameters, which you can think of like global variables that are specific to templates. Let's add a sample percent parameter containing 10, for example. In the template form, we can access these by prefixing the parameter name with a $sign. This is useful when using multiple templates and you want to share some common parameters. For example, if we had used this sample persons template multiple times in the same code workbook, and we want to sample in the same way across all the different uses of the transform. Let's run this template node to finish out this example for completeness, naming the result condition occurrence sample. To use the intermediary sample dataset as input to the downstream transforms, I can simply update their code to reference it. Notice that when doing so, the graph edges update to indicate the new dependencies. Downstream transforms that are saved as datasets do need to be rerun to get their results updated. Note that it's possible to trigger reruns of downstream datasets via the drop-down next to the Run button, and under the gear icon up top you can run all saved dataset transforms in the notebook. The new input after we've changed it is coming in as a Spark data frame, so we'll also need to ensure it is converted to an R data frame, since that is what we wrote this code to expect. Although we don't have time to cover it here, it is possible for you to convert a transform node or even multiple transform nodes into a template, and then contribute that template to the N3C knowledge store for others to find and use. If that interests you, the trading portal contains a templates quick start guide and information about the knowledge store, and we've discussed both the knowledge store and authoring templates at Enclave users group meetings, recordings of which are also indexed in the training portal. The sample persons template we imported from the knowledge store was very simple. Let's see an example of using a more complex multi-node template. First, we'll open the knowledge store application from the main Enclave homepage, which displays all of the templates and pre-computed datasets that have been contributed by the N3C community. The Data Provider Robustness Matrix template is a good example of such a complex multi-node template. Clicking on it, we can see a short title and description, links to projects that have used this template, and links to README documentation and the template itself. If we open the template from here, we can see that it requires a number of input parameters, and if we click on Nodes, we can see links to individual transform templates that make up this complex multi-node template. Back in the Overview tab under Actions, we have the option of using this template in a brand new code workbook. Instead, let's use it in our existing code workbook. Since I'm not sure of the input datasets yet, I'll create a new transform button rather than applying one to an existing node with the blue plus button. This creates a node with no connections, and I can use the templates option to find the site quality grade template. The search functionality works well for finding templates by name. In the matching results, the three little blue boxes next to the template indicate that it is a multi-node template. When I select it and click Apply, all of the nodes comprising the template are added to my workbook. Let's zoom to fit quick to see all of the nodes that have been added. Once the template has fully loaded, we can select one of the nodes to start working with it. Since we've already imported the condition occurrence dataset, let's start with the condition occurrence check node. This template node requires that I choose an input for the condition occurrence parameter. Let's select our sampled occurrence table. It also needs the manifest table. We'll have to import that one first, and again we're going to grab it from the Cynthia data collection. The manifest table, by the way, is an N3C specific dataset providing metadata about each N3C data partner. Since this big template is designed to build quality check graphics, it uses the manifest to help break things down by data partner. Like the rest of the data in the Cynthia data catalog, the information in the Cynthia manifest table is completely fictitious. Before I actually select the manifest table as an input to that node, let's take a closer look at the other nodes that got imported as part of this multi-node template. For example, the drug exposure check node wants a drug exposure input and also the manifest input. Same deal with other nodes. Right above the inputs, we can see that this node is part of a group of nodes belonging to the multi-node template we imported. If we click on View Group, we can see all of the different nodes involved. We can also color the nodes, which I like to do to help me keep things straight. Further down in the group, we can see all of the different input parameters for them all. And even though the manifest table is needed by lots of the nodes, it is only listed here once. This is a shared input in the multi-node template, and it's something the author set up to help make the template easier to use. Because this is a shared input, I can either set it for all of the nodes that need it here, or set it for any particular node in the template group, and the rest will get it as well. This multi-node template has lots of input tables it wants. I'm not going to finish this example out because all this template does is compute some summary statistics for all of the data, and we're working with mock data anyway. This is a good time to mention that it's also possible for templates to automatically import required datasets, and many templates in the Knowledge Store do this to save us the frustration of having to import them all individually. However, this means that a template that automatically imports Level 2 or de-identified data cannot be used in projects that don't have Level 2 data access, including projects that have Level 3 or limited dataset access. This is why you will frequently find multiple versions of templates available in the Knowledge Store, each of which includes different automatically imported datasets. And with that, we'll conclude our introduction to Code Workbooks, a powerful multi-language tool for data analysis in the Enclave. Before we go, I just want to briefly mention a couple more advanced topics in case you want to investigate them more. First is branching of both Code Workbooks and the datasets they create, allowing the management of different versions of data and code. Second is the ability to export a code workbook to a code repository, an Enclave tool with more software developer-focused features like pull requests. Finally, there's the usage of the data lineage tool, also known as Monocle, where you can inspect the relationships between datasets and the code that creates them, both within and between workbooks and other tools like Contour and code repositories. Have a good one, and thanks for watching!